So this is a simulation. This is a website. I can post the website link on Facebook. I already have, actually, if you want to go look at it sometime. This is just a website, and you can go and play with it. What we have here is a model of the Bohr atom, and up here we have the nucleus. There in the center we have a blue thing. Oops, I need to reset everything, don't I? There we go. Boo boo. All right. So now you see the little blue thing in the center ring in the ground state. What do you suppose that blue thing is? It's an electron. It's an electron, and it's currently in the ground state. And I want to kind of just introduce you to the different parts of this visualizing tool before we get too deep into it. But this, there's my blue thing. There is the electron. It's going around in these circles around the nucleus. And what we're going to end up doing, as we saw in the demonstrations, we're going to shoot light in and have light come out. So we're going to emit and absorb light. So up here we have a couple of spectra. This is a spectrum. This is an absorption spectrum, and this is an emission spectrum. You probably, if you're in school watching me right now, you probably can't read the words emission and absorption there unless you're in the first row. But if you're watching this at home, you might be able to see that. But this is an absorption spectrum up here, and this is an emission spectrum down there. We'll see what that means as we proceed. But the first thing that I want to call your attention to is the order of the spectrum as it's shown on this. What do you notice about it? It's backwards. It's backwards from the way we learned it. Now, that's nothing big or deep or fancy. That just means that whoever made this simulation thought it would be better to show it this way. Now, what we learned doesn't change. Red is still the lowest energy visible, and violet is still the highest. So what happens to energy as we go on here? Energy gets bigger, and when we go which way? Left or right? Left. So everything we've done so far, energy gets bigger as you go to the right, but on this particular way of looking at it, energy is going to get bigger as you go to the left. So remember that. Okay. So instead of Roy G. Biv, we got a little Vib G. Yor. Does that work? There we go. Okay. Also, to the ends here, we have IR and UV. Not all of the photons that are going to come in and out of this atom are visible. Some of them are infrared and some of them are UV, but just remember that those can happen, but you won't see them. I mean, you might on the visualization, but in the real world you wouldn't. Yes, question? Oh, the question is, why did the electron quit moving? The answer is simple. When I write on the board, it freezes anything that was on the screen. And so whenever I close the layer, which I'm about to do actually, I'll close the layer, it should start going again. There you go. So yeah, that's just a matter of anytime I start writing anything, it freezes everything. But so now we're ready to go. So what I would like to do now is I'd like to see how the simulation works. I have some settings over here. It says current orbit here and destination orbit. In other words, I have the orbit that it's in, number 1, and the orbit that I want it to go in, which I'm going to set that at number 2. In other words, I'm going to have it jump from 1 to 2. Now, in order to jump from 1 to 2, what's it going to have to do? It's have to get energy in the form of light. So in other words, if I hit jump, a little photon of light will have to come and hit the electron and bump it up. So let's watch that happen. And 3 and 2 and 1 and... Okay, it did it. Now what color made it happen? Green made it happen, correct. So if I go from 2 to 1, what's going to have to happen? If I go back down, what's going to have to happen? It's going to, instead of absorbing, it's going to shoot out or emit green. Now before I do, notice up here, this is going to, see this guy right here? What's that? There's a black line there. This, remember, is the absorption spectrum. So this is showing you what color was absorbed there. It absorbed green to do that. So that's why there's a black line there to show this is the color that was absorbed. So this is an emission spectrum below it. Down here we have an emission spectrum. So in other words, whenever light comes out, it's going to show up down here. So if I go from 2 to 1, if I jump from 2 to 1, which I'm set up to do as soon as I hit jump here, what should happen? It should show up, it should give off a green. We should see a green right there, and there we go. There it went. There you can see that. So we absorb and we emit. Now if we go from 1 to 3 instead of 1 to 2, what would your prediction be about how we could make that happen? So someone guessed violet, someone guessed blue. Those are both reasonable answers. You don't know exactly what it'll be, but why do we know that blue and violet are good answers and that red and orange are bad answers? That's right. If you go from 1 to 3, that should take more energy than 1 to 2. So we should expect energy more than green, and examples of that would be anything over here, anything in the blue, violet, ultraviolet. So let's just see what that is. If we go 1 to 3, we jump, we absorb. Happened to be UV, which was what we predicted, something higher energy. And if we go 3 back to 1 again, we would shoot off that same UV, so we would emit UV. How about 1 to 4? If 1 to 3 took UV, what would 1 to 4 take? Well, presumably it could take X-ray. However, one of the things that we'll find was with regular atoms, just for electrons bouncing around between energy levels, it's usually going to be somewhere in the infrared, visible, or UV. That's just kind of the energy scales that we're usually dealing with atoms. And so, given that those are our choices, what would you guess? UV. But there's a lot of UVs up here, right? So you would guess that a UV that was further to the left, further something over here. So let's do that. Let's go 1 to 4, and there it is. It's just like we predicted, just to the left. And if we go, oh, so look how fast he's going now. If we jump back down 4 to 1, we should emit that same guy right there. All right? Is that, so we went 1 to 2, 1 to 3, 1 to 4. Does that represent all of the possibilities? No. What about, we could go 2 to 3, couldn't we? 2 to 3. What is your guess on 2 to 3? But before you do guess, let me tell you something that you don't know now. When you visualize these steps, you're probably visualizing stairs like we would have at home or in the school, just regular stairs, right? Well, atoms, the energy levels here actually don't work that way. They're actually a little bit more complicated. The first step for an atom is not a small step. It's actually a bigger step. It's like that. And then the second step is actually significantly smaller, and the third step is still smaller, and then they get smaller as you go, and it's kind of like that. So given that the steps get smaller every time, any predictions on what 2 to 3 will be? Should be medium. So 1 to 2 gave us this green color, right? 1 to 2 gave us this green color, so 2 to 3 should be more than or less than green? Should be less than green, so we would expect something to the right of green, something like yellow or red or infrared. Let's see if that's true. Hope it is, or I have to start over my video. Oh good, it worked out for us, didn't it? What color was that? We absorbed a yellow, so if we go back 3 to 2, we shoot out, we emit a yellow. What about 3 to 4? What's your prediction on 3 to 4? Let's go to 3. Oh shoot, I skipped ahead, didn't I? Well, let's pretend we didn't see that. So let's go back to 3. 3 to 4. 3 to 4 is going to be a small one, so you would expect something way over to the right, something in the infrared range, and that is what we get. In fact, if you look up here, I'm sure you in class cannot see that, but it says exceeds max display. In other words, this spectrum that they're showing only has a certain number of energies, and that's actually lower than any of these, so we weren't going to show it on there. You with the question? Did I notice? Oh yes, the wavelength bar does change color. Thank you for pointing that out. Yes, this guy right here will show you actually the color that was emitted or absorbed, and actually the actual numerical wavelength. In this one's giving it in nanometers. So we would expect, if that one we just gave was really small energy, 1287, if we go back and look at, say, the violet one or the ultraviolet one, you would expect the wavelength to be bigger or smaller for a high energy? should be smaller. So if we go back and look at one of those, let's do like the 1 to 2. These are all smaller. So there's I believe that was 3 to 1 or 1 to 3 that I just did, and the wavelength's all the way down to 300 compared to the 1400 we had a second ago. So the bar shows the color, but also gives the numerical value of the wavelength. So that's kind of cool. So I'm going to go ahead and stop that, make a few other points, but this video is getting a little long.